continue vector functions. What we learned so far? We learned about a vector function, v of t, representing the position of a particle, f of t, g of t, and h of t. Since we have a function, we said that, hey, we have the domain of that function. By finding the domain of each of these components or scalar functions, we can find the domain of this vector function. Then we actually found the limit of the function. We said that the limit of the function exists if the limit of each of these scalar functions exists as well. We talked about continuity. This function is continuous if the limit of the function is equal to the value of the function at the given number. Okay, then we talked about the derivative of the function. When we talked about the derivative of the function, we talked about the tangent vector. And after we talked about tangent vector, which is tangent to the curve or space curve of that function, we say that we can scale that and we have unit tangent vector. Well, some properties for the derivative of the function. Let v write r u and v. So let u and v of t be vector functions. And suppose they are all differentiable functions. C is a scalar and f is a real valued function. These functions are differentiable in their given domains. C is a scalar or a number, and f is a real valued function. They have the following properties. The derivative, or if you differentiate the sum or difference of these two functions, u of t plus or minus v of t, it means that we take the derivatives or we differentiate these functions respectively and we add or subtract the results. This is equal to d dt of u of t plus or minus the differential of the v of t. So what if you have the product of a scalar or a constant with your function and you want to find the derivative or take the differential of c times u of t? So in this case, you can just take this constant and write it in front of the differential. C times the derivative of your vector value function. In the case that this is replaced by a real valued function like f of t, and you want to find the derivative f of t times u of t, this is equal to, you're actually applying the product. We say that, hey, we have the derivative of f times u of t plus the function f(x) times the derivative of your vector valued function. So what we learned in elementary calculus using the product. So now I expect you to ask, what if I have the multiplication of two vector valued functions? So in this case, again, we apply the product, the differential of u v is equal to, remember that you have to form the dot product, is equal to the derivative of u dot v plus u times the dot product of the derivative of well, what if we have the cross product between the two vector value functions? Well, so this is number 5. If you have the cross product between u and v, remember that these are all vector functions. It means that we can actually form the dot product and also form the cross product. But how do we take the derivative of the cross product? It is equal to the derivative of u cross v. So the derivative of u cross product v plus, now we were just going to write down u and take the derivative of v plus u cross product, the derivative of v. So in a sense, it's similar to applying the product rule, but note that here we have the cross product between them. And what if we have the composition, the derivative of composition of u and real valued function f? So we have composition of two functions. Composition, it means that we need to apply the chain rule. The chain rule says here it is equal to the derivative of f times the derivative of u composed with